Welcome back, and let us try to complete our discussion on sizing for the second amplifier or the variable gain amplifier for our front end. So, once again I had the same op amp circuit over here, and we tried to distinguish the high level specification, and for the time being I have taken some simplified assumptions just to focus on some of the more crucial points. So, I have assumed that the load capacitance over here is similar. Even if it is different, then only difference it will make in the constraint over here is will determine a different value of GM1, GM2 based on the gain bandwidth product. So, that is not a crucial factor. Let us assume that the load capacitance faced by the second stage is also similar, and that means I am going to have again the same gain bandwidth product requirement for the second stage, and that is going to have similar value of the CL and CC, and likewise the GM1 and GM2. So, since I was assuming CL to be similar, the CC also comes as similar, and following the area constraint I would like to have CC half of CL, and then based on that I need the values of GM1 and GM2. So, that calculated I have the GM1, GM2, and also I have the current budgets available. Total current budget, I said that okay, let us reduce the current in the second amplifier. Rather than going to 40 microampere total current, I can go down to say 10 microampere, because my noise requirement is not so critical. I can afford to have relatively higher thermal noise as well as 1 upon f noise corner. So, I assuming those things, I can reduce the ID2 and ID1. Let us keep them 2.5, 2.5, total current budget around 10 microampere for the overall second stage amplifier. And then as a result, of course, I will have to decide what is the ratio of this bifurcation, what should be the ID1 in the first stage, what is the ID2 in the second stage, and there also it will lead to the corresponding ratio of W by L 1 and 2. In the first amplifier design, I did not consider the ratio of this W by L 1 and 2 so important. I just allocated same bias current in the both the stages, and that would mean that the W by L1 and W by L2 ratios are also going to be similar, determined by this GM ratio. So, because the GM of one of them is half the GM of the other, the W by L ratio will be correspondingly 4 times. So, that was the deciding factor over here. Now, we know that for the second stage amplifier, one of the very important constraint will be the output swing, because if we look at the number that we are using, input signal say 100 micro volt, the overall gain 10 to the power of 4, overall closed loop gain of the first stage 100, second stage 100, 10 to the power of 4 overall. So, the final stage over here, the signal over here that we are getting, that can be having a overall signal swing of 1 volt peak to peak, right, 100 micro times 10 to the power of 4. So, I can expect even up to 1 volt peak to peak signal worst case, and I have to make my output stage such that it is capable of handling such a large signal swing. And to do that, I have to look at the sizing of these two transistors carefully for the given current budget. Now, in order to look at the sizing, if I want a better swing over here, I would like to have a smaller V over drive for this. Remember, what is the maximum and minimum voltage that you can have at the output? VDD minus V over drive of this PMOS is the maximum, and the minimum side just V over drive of this NMOS. So, in order to get better swing, all I need to do is minimize the V over drive of the PMOS and V over drive of the NMOS for the output stage. How do you minimize the V over drive? So, V over drive, as I remember, it depends upon the ID and W by L, because ID is equal to W by mu n CUX W by L times V over drive square. So, V over drive is equal to root under ID upon W by L. So, I can write it down for the output device. Keeping the amplifier circuit same side by side, let us look at the V over drive of M3 and M4, both of them. I can write down ID of the second stage is equal to 1 upon 2 mu P COX W by L. I can call this M3 because it is just I have marked it as M3, the W by L3 times V over drive square, which is VSG minus mod VT of this. I want to minimize this, and therefore I have two options: either I reduce this, or I increase this, or I can take the combination of both. So, since the requirement is to get a certain GM, I need the product of root under ID W by L3 to be having a certain value. So, I need root under ID2 ID2, which is the total bias current in the second stage, ID2 times W by L3, that is determined by the GM3 that I already, or the GM2 that I already have. So that GM2 is already determined from the gain from this product requirement. So this number I have, so this product must be maintained. So if I am trying to reduce my V overdrive to get the better swing, either I reduce the ID2 and increase this, that will help me in maintaining the ratio, and therefore I can go for half the current. I can reduce the current in ID2 to 1.25 rather than 2.5, and correspondingly increase the W by L3, and that will keep the ratio of GM2 same. So I have a similar ratio, only thing is I have been able to reduce the V overdrive. So that strategy can be used to have a better signal swing on the upper side. So I can trade off the bias current over here. Now if I look at the lower side, once again similar constraint is going to come, because we know that V out min is going to be equal to Vg4 minus Vt, and therefore basically V overdrive. And once again, in order to reduce V overdrive 4, I would like to make the W by L4 larger once you have the ID determined. So suppose I reduce the ID of the second stage to a smaller value, maybe 1.25 microampere. For that I can determine what is the required W by L of M4 to get a certain overdrive. So this is going to determine my W by L required for M4. Now the ID 2 is known, so this is going to give me the required value of RO to get the GM2, and hence the value of L of the PMOS and NMOS. So ID2 is going to give me the RO2 required for the overall gain in this stage, and if I assume that the gain is still equally divided, which is not necessary, I can sacrifice the gain also over here a little bit, because I am trying to reduce the bias current, or as in other words, I can try to increase the gain over here a little bit so that it supports the reduction in bias current. But assuming that we are keeping the gain division almost similar, so once again I can have a overall 100 gain in the second stage, and that is going to give me the RO value for the given GM2 value for a A2 equal to 100. So for a given A2, I can once again find out the RO2, and hence L3 and L4. Ultimately L3 and L4 determine the RO2 for the given chosen current, and that is going to give me L3 and L4, and W by L3 and W by L4 I have already determined. So I can from there obtain the W of L3 and L4 from the earlier quantities. We can obtain the W3 and W4. So here we looked at the sizing of W3 and W4, and we notice that here the output swing is becoming a major constraint, and based on this particular constraint, we are looking at other related issues, that okay, based on the output swing you first determine the W by L ratio so that you are able to maximize the output swing. Based on that only we are trying to minimize the current over here, reduce the current in this branch as compared to the differential pair, so that my overall swing over here is maximized. So I took two steps. I reduced the ID2, that is the total bias current in the second stage. I also tried to increase the W by L3 to have the similar GM in the output stage. So that those two things we have maintained, and then of course the L I said can be determined based on the RO requirement, because I have the gain requirement A2. Based on that I can get the RO2 and hence L2, and then therefore W by L of these two can be determined. Now also we have to see the sizing constraint, how it has changed for these two devices. For the input devices we have already seen, there the constraint is similar. You have the W by L determining the GM1 and hence the gain of the input stage, because now we have relatively larger bias current available over here. If we want to use the same bias current, total bias current allocated, so I have reduced the bias current here, therefore I can use a slightly larger fraction of bias current rather than 2.5, I can use 3 or 3.5 microampere current here total. And based on that, I need to look at the W by L ratio of this one, and also the L ratio, the L value determines the RO. So, here the GM determines the W by L and the RO determines the L. So, here the constraint remains similar, but for this device once again the constraint is going to be slightly different. Here the L2 is not an important constraint, because 1 upon F noise corner or thermal noise frequency is not going to be an important constraint. Therefore, we would like to rely on M2 to facilitate better output swing over here. Remember, first of all, we have increased this W by L so that the VSG required for this device is going to be smaller, and therefore we are expecting that DC point over here will be larger, and if the DC point over here is supposed to be larger, remember we need to have a smaller V over drive for this MOSFET, because if the DC point over here is supposed to be larger in order to facilitate more output swing at the final stage, I need to have a larger DC bias point over here. A larger DC point here means higher maximum V out, because maximum V out over here is Vg plus mod Vt. So, a larger DC potential here means higher maximum swing over here, and a larger DC potential over here, higher DC potential over here means a smaller VSD or a smaller V over drive, and a smaller V over drive would imply a larger W by L. So, I would like to have a larger W by L of this device. So, the constraint on W by L becomes more important. I would like to have sufficiently large W by L for this device in order to ensure a smaller V over drive. Remember, in the common mode feedback that we have studied, how did we bias this? This was biased with the help of a, if you are going for a separate loop, there it is biased with the help of a common mode feedback amplifier with reference equal to the Vg of this MOSFET or Vg of this MOSFET. And in this case, since we are expecting a larger DC potential over here, we would like to have the Vg over here also higher, and that would require a larger W by L. So, that is the difference with respect to the earlier case, some of the constraint getting relaxed and some other constraint coming in to determine the overall sizing. So, and likewise we have the similar constraint for the M5. Here once again input swing is still not an important constraint, because these 2 points are still DC bias points. You are having these points close to VDD by 2, so you do not have much signal at this point. Therefore, the M5 sizing constraint remains similar, there is not much change. Output over here, if you look at what is the swing at this point, once again output swing over here close to 1 volt, 1 divided by 100, so you have at the max at 10 millivolt swing here. Therefore, once again here also swing is not going to be very critical. Output swing at this node is once again still not critical. So, we should just be careful about what constraint or what parameter is critical and what is not, and based on that we can determine how to size, and while getting advantage in terms of saving some bias current while not messing up with any other specifications. So, these are the I have just presented some logical steps to facilitate sizing of the front end amplifier and the second stage variable gain amplifier. So, this is another issue that we have is the common mode feedback amplifier. There we have already studied that for the common mode feedback amplifier, if we are going for a single loop and we are not we are using the diode connected load for the error amplifier, there of course the gain requirement is not so critical, and therefore the W by L and bias current all can be relatively lower, sizing constraint can be relatively lower, and also the error amplifier output comes over here as a common mode, and whatever noise output is coming from the error amplifier, that is also appearing in common mode. So, the noise consideration for the fully differential operation will still be relatively constrained for the common mode feedback amplifier. Therefore, even for the front end amplifier, when we are discussing the sizing of the common mode feedback amplifier, the noise constraint will be relatively relaxed. We may not really worry a lot about the common mode feedback amplifier, because just like the current source contributes in a common mode fashion, likewise the common mode amplifier noise over here will also contribute in a similar fashion. And if we look at the input, if you look at the common mode feedback for the joint loop, like if you are having single loop and if you look at the common mode of the individual loops where you are requiring larger gain for the common mode feedback amplifier, there of course you are using current mirror load for that, and we are assuming GM-RO gain from the common mode feedback amplifier. There some of the constraint related to the common mode feedback can be the input swing, means what is the input swing that the common mode amplifier can handle. So, one of the important points that were discussed in the simulations also is related to the input device dimension, the GM of the input device. So, if we are using say in dual loop common mode feedback where we are relying on the diode connected load, and this is your VO plus and VO minus coming, and this is your VREF. One of the important constraint would be of course the gain. We would like to have sufficient loop gain, so GM-RO product should be sufficient, and also we need to have a sufficiently large RO over here so that the compensation does work. Remember, for the common mode feedback, the compensation point is this one. We are creating a dominant pole over here because we add the capacitance between the output of the common mode feedback and the output of the differential pair. So this node gets compensated. Now the other point is the values of the devices over here, the W by L sizes over here, and that is going to determine this overall GM-RO product of this particular stage, and whether we can rely on a larger RO or larger GM. Once again, larger RO, it will be favorable because larger GM for input devices can negatively affect the maximum swing that the input devices can handle. So if you rely on larger GM, that means the overall signal swing that the input transistors over here can handle, that will be relatively lower. If you look at the differential pair response and look at the current ID1 and ID2 in the two devices, say M1 and M2, as a function of say VO plus minus VO minus, suppose this is 0 and this side we have positive VO plus minus VO minus, and of course as a result ID1 will be going higher on this side, and as you make the VO plus VO minus negative, the ID2 will be increasing and ID1 will be decreasing. So this is your ID1 curve and this is your ID2 curve, and smaller. So this slope in this particular region, this transition region, is determined by the small signal transconductance of these two parameters, which is also related to the transconductance here. So in order to get proper common mode feedback extraction, we would like to have the GM1 plus GM2 equal to GM of this, and therefore if you want this error amplifier to handle a larger common mode, we would like to make this slope relatively poor, and hence that would imply that we should have a poorer GM of these devices. So that will ensure that it is able to handle a larger VO plus VO minus, especially if your output signal is becoming large, peak to peak signal is 1 volt, and you want this to be handle to be able to handle that large signal. We would like to go for a larger input handling capacity, and that can be achieved by significantly reducing the GM. That can be achieved in two ways: either you reduce the W by L or you reduce the bias current. So if you reduce the bias current, RO automatically will be increased, and hence the gain can still be sufficiently large. And remember that the GM-RO product increases by root under K. If you are reducing the bias current by K, the GM-RO product root increases by root under K. So that will still increase the gain. However, it will suppress the GM, and hence it will try to increase the swing that this input device can handle. So that is another important feature that we should consider while looking at the sizing of the common mode device. And also another point will be to size this tail current source. So if you make the tail current source sufficiently large, it will be able to handle a lower input signal over here, and that also increases the maximum swing, the differential swing that the that the common mode device can handle. That is another way, and we can have other alternatives also in cases where the output signal swing is sufficiently large and extraction of common mode using this scheme is failing, we can go for other schemes where you can have you can handle larger output signal and where it is not constrained by such a differential swing. So we can take 2 minutes break. After that we will resume the discussion.